we have our main speaker here. I'm very proud to present Professor Robert Dominko from the National Institute of Chemistry in Slovenia. And I look forward to your questions. At the end of the lecture, you will be able to send in questions in the Q&A, and I hope we can have an inspired discussions. And we have all our excellent seminar in a library on YouTube. You find it if you go into our webpage. There you can find the previous excellence lectures. And next excellence lecture will be 27th of October. And that will be Margaret Wolfers-Ferens from ZSW in Germany. But now I leave the floor to you, Robert, and we look very much forward to this, to listen to you and to discuss science with you. So welcome.
Thank you, Kristina, and thank you for this nice introduction to the field of smart functionalities and smart batteries. And that's actually quite natural choice why I selected this as a topic today. Just give me a second to arrange the presentation. Okay, so I'm happy to be here, and I'm happy to actually to share with you our latest results that we obtained in my lab and working on self-healing coatings. Those self-healing coatings are mainly devoted at the moment to lithium metal, but also to magnesium metal. And also in the second part of my talk, I'm going to talk about electrochemical sensor printed on the separator. But before I start, and I'm quite sure that I will be late, so I would like to start with acknowledgement, with contribution. So Dr. Nates Pauline, he's already out from my group. He's employee of one in the private company, but he actually the work that I'm going to show today based on the cellulose and coatings based on the cellulose, that's his work. And then this group of Tina Palk, Dr. Victoria Bracamonte, and Professor Dr. Tomasz Sirovi, they actually designed and worked with me on printed sensors, electrochemical printed sensors for electrochemical detection of dissolved ions in the electrolyte. So Victoria is currently in University of Cordoba in Argentina, and Tomasz Sirovi, he is a professor at the University of Pardubice. And of course, I need to acknowledge also greatest inspiration from Battery 2040 Plus and also Slovenian Research Agency, which actually supported all this work that I'm going to show today. I'm actually an employee of National Institute of Chemistry, but I'm also a full professor at University of Ljubljana. So this dual position allows me to attract also a lot of young people into my group, but also to create a good stimulating environment and exchange ideas between university and research institution. So NIC, if I can shortly name our institution, we are divided into 5 different large domains covering all thematics that are currently hot topic, from life science to energy projects or laboratories that are working on the energy securing projects, analytical chemistry, computational chemistry, and engineering science. So those data are from December from 2020, but currently we still have 6 ERC grant holders inside our community. A lot of already Horizon Europe program projects, and also some other pre-European projects, and so of course some Slovenian foundings as well. My group actually is around 25 staff that are on the pay list, and then several university students, master and bachelor degree level, who are working with us on daily basis or occasionally when they have time. And we are very well equipped for battery research up to TRL 3 to 4. but just recently we secured a nice grant which allow us to build also new battery center that will actually enable that we move our activities up to maybe tier 6 to 7, and this is planned to be in function in 2024, maybe 2025. So just a few more words about us. As you know, we are quite very well established group worldwide, and we are also heavily active in Alistor REI. I'm one of the deputy directors there. We are actually now involved in 7 European projects, but in the past we also did some coordination of actually I was a project coordinator of 2 European projects. What I'm proud and what is very good connection that we are actually connected also to the students for the MES Plus program. This is Erasmus Mundus Marie Curie program, and also Destiny doctoral program. Again, Marie Curie supported the doctoral program from your commission. And of course, as any battery lab today, we have also industrial collaboration. A few more words about our research activities. So we are divided into several thematic domains, but also those thematic domains are not equally represented. Right now, there is a lot of activity on sustainable materials, especially on the post-lithium-ion batteries, post-lithium batteries working on magnesium, aluminum, calcium, organic cathodes, sulfur-based cathodes, even also some activities on aqueous batteries. We have activities also towards the all solid-state batteries, supercaps, understanding and designing composites, battery composites. And what I'm going to talk today, this is right now minor activity, but important because I will show you our activity on sensors and on self-healing functionalities. In future, with the battery center, we are aiming also to move into this direction to recyclability and second life. And this is then covered with 2 cross-sectional activities, modeling, mainly one lady behind with students, and instrumental methodologies with all equipment that we have and we can use on daily basis. So this gives us a lot of opportunity to be really front runners on different directions, and our everyday discussion is whether we work on the preventive actions or we actually design curative actions. So preventive actions, those are actions to design better materials, to design more predictable materials, to design better interfaces, higher stability, thermodynamic stability, kinetic stability, to understand those phenomena and actually to modify active materials, components, non-active components in terms to act preventive. But as we know, each battery works in different environment, it works in different conditions for different purposes, and sometimes, and even cells from the same batch are not exactly the same. And I'm comparing this as humans. We are equal. We are look the same, very similar, but we are not exactly the same. So that's also is happening with the cells. And from time to time, we still hear some problems that are occurring, and some people are not happy with battery technology because it doesn't last enough, or maybe because of the safety or because some other points. And for that, we need to develop also curative actions inside batteries to somehow to be able to predict the degradation, and then maybe as with some medicaments and some curative approaches also to heal degradation or to cure degradation and to prolong battery life. That's the general idea behind, and we have seen this idea is actually built by Battery 2040 Plus initiative, but in the last lecture that I saw from Hong Li from Chinese Academy of Science, it's already heavily implemented into Chinese actually everyday research activity. So Lithium-ion batteries are nowadays all around us. We almost cannot live without them. And we know that each battery has a certain period of time, but maybe in this portable electronics, batteries lifetime is shorter. In electric cars, lifetime is extended, and our colleague Jeff Dunn is already talking about the 1 century lifetime of lithium-ion battery. But still, we know also about degradation processes that are occurring inside. And those degradation processes can be actually divided into different sections, which can be mitigated by some additives, with running battery in specific conditions, in specific temperature, voltage window, and so on. But some of them, even that we are doing really the best, it's hard to mitigate. And that's why now actually we are moving to the chemistries that maybe are not so problematic. And that was also motivation in my group. So we know that first electric cars were actually using lithium manganese oxide spinel structured material as a cathode or as a cathode blend material. And then companies slowly moved to NMC and nickel-rich materials. But with the increase of electric vehicles, we can expect that there will be again shift back to manganese, and it will be necessary actually to understand manganese dissolution in the electrolyte and also to monitor its dissolution, to be aware of the state of the life and state of the health of the battery. So this is this will be a second part of my talk. But before going to the second part of my talk, I would like to actually go more into self-healing, and also to explain you why self-healing is necessary. So the whole idea, also Kristina explained, is to have this smart battery with sensors, with self-healing, triggered possibility for self-healing, and we can monitor through the sensors, and then through artificial intelligence we can actually trigger self-healing, and by using also BMS. So this is somehow with that we can increase battery reliability, safety, cycle life, and even that we might increase the cell cost at the time of purchase, but we can for sure we can lower the cost per kilowatt hours of stored energy, and also we can reduce environmental footprint, because recycling and then reusing of the components will be less possible. And with that, actually, I'm coming to outline of my talk. So as I mentioned already a few times, first part of the talk will be on stable coatings on metallic lithium. And if you go more deeply into these coatings, we saw that there is even a big European project working on formation of stable coatings. That's mostly research topic in almost every lab. And we can actually see that if you are going back to 2001, and that figure was for a long time like a leading figure on many scientific talk, that lithium is unsafe. And still today you can see some students are coming, okay, but lithium is unsafe. But somehow we know that we are moving also into the direction of using lithium metal. Why we are moving into this direction? Because we can expect that by using lithium metal, we can expect more powerful and more rich, energetically rich batteries. And that means actually that is worth to explore and worth actually to learn what should be done, and also then to implement that into commercial cells. There were several proposals in the literature. There is hundreds and hundreds of papers which claim that they solved the issue, and I'm one of them. I would claim again today that might be a solution. But these proposals can be actually divided into the 5 different topics, and one of them is actually formation of artificial interlayers coatings, which has to be ionically conductive and electronic isolating layers at the interface. And of course, it has not, or it should not bring too high resistance for ionic conduction. So we start to work on that, and the first actually attempt was with a student on fluorinated graphene and graphene oxide, but then we moved to one polymer which should be very good ionic conductor for lithium. This is so-called tampeta, and somehow we observed, okay, it works better if we have this layer on the top of the cell, on the top of the lithium metal, compared to the non-protected lithium, and moving from 0.5 milliamp hour per square centimeter to 1 milliamp hour per square centimeter, we can see even better. We see some polarization in the first cycle, which means that there should be a formation of ionically conductive pathways, and that's it. So stopping here, we would be actually happy, and we can publish this. Okay, great results, good proposal. But we wanted to know more. So we opened the cell, and of course, opening the cell where lithium was not protected, it is expected that you see this black coverage of the lithium metal, where this high surface area lithium is formed, and going to higher current densities that can create also dendritic growth. On the other hand, electrode that was covered with tampeta remained metallic shine, and okay, but this is good sign, so maybe that's actually a really protective layer, but edges were highly damaged and also disappeared edges, as you can see here. And that's a clear signal, okay, this area that was actually covered with tampeta was not electrochemically active because there was too high resistance, or there was slightly increased resistance on that area, and that actually correlates all electrochemistry on the edge. So our first goal, and that actually was covered then by SEM and also by XPS, but I don't have time to go deeper into this. So that was actually giving us hint, if you want to study really this and to have a reliable studies, we need to design a cell which can protect edges, and where edges actually are not active, if since we know that sometimes it's very hard to protect edges also with this protective layer. So that's we designed actually at the beginning. We have used the polypropylene disc, which was pressed on the separator. Now in the new modification of the cell, it is enough that we press with a special tool the edge of the separator, and that actually creates a non-permeable area for lithium ions, and that actually prevents also extensive electrochemistry on edges. And now that the situation is actually different. Now you can see we have higher polarization as we expected from the beginning, but this polarization then is increasing more on the area of where tampeta is more in the area with electrode with tampeta compared to the electrode with which was not covered. And then looking to electrodes, both electrodes, we see that this conductive or this protective layer actually didn't have any function, because the polymer, it seems that polymer didn't sustain the cracking, and then we can observe formation of high surface area lithium. But that's a nice example how actually community have to be aware of doing and carefully experiment, and that gave us also a nice tool for continuation of this work. And in continuation of that, our work, we moved to the cellulose. Cellulose, we know that this is the second, the polymer that is the second most abundant in the Earth crust, and we actually every year we can have more and more production, and depends then on how many trees we cut. but it is used in the paper industry. So paper industry is used to work with it. And that was somehow our motivation to start to work on cellulose, and we moved to this nanofibrillated crystalline cellulose. And first concern was, how about with water, content of water inside the cellulose? So we know that cellulose is hydrophilic and it attracts a lot of water without any additional drying. Just if you have dry mass of cellulose, but still contains around 5–8% of water inside. But with careful drying, you can really decrease this quantity. And then the next problem comes when you deposit cellulose with weight laying procedure, which is used in the paper technology. Paper technology wants to have a less porous system, but we need some porosity if we want to have electrolytes filling this porosity and to have some kind of conduction for this porosity. That's why we also started to use paraffin oil, which created porosity and which give us also nice playground to adjust porosity and adjust thickness and so on. And working on that, we can see some improvements, but still actually opening the cell, and we still see that after 500 hours of working, lithium metal is not degraded so much if it's in the contact with the cellulose as compared to only with Celgar separator. But that's not actually what we were looking for. For that reason we actually looked we moved further. Also here, actually, we saw that this degradation from FIP was stopped, was not so heavily degraded, but anyway, we see this high surface area lithium formation on the surface of the lithium, and that means that sooner or later there will be intergrowth of the dendrites through the cellulose and might create short circuit with the cathode. And that actually brought us to the next step, and we start to think, okay, but how to deposit cellulose directly on the metallic lithium? And of course, if you have cellulose which is hydrophilic, you cannot dissolve it in solvents which are compatible with the metallic lithium. For that reason, we decided to modify cellulose, and we form 3-methylsilyl cellulose, so-called TMCC. And this one is soluble in THF, which we know that it's compatible with the metallic lithium. And by careful modification, we can exchange 3 OH groups that are here with 3-methylsilyl cellulose, and we can create more or less completely silinated cellulose. And that's one of derivatives which we are using, but we are developing also some other derivatives which can be adapted even to shift from liquid electrolyte to polymer electrolyte and so-called all solid state configuration. Anyway, this silinated cellulose, if I can call it in short, gives much better results, but still keeps some kind of porosity inside. And if you fill that porosity with electrolyte, then the electrolyte has direct contact with the metallic lithium, and that creates a problem. But then there was a next step. Actually, we filled the porosity with lithium salt. And the idea was actually to fill it with lithium nitrate at the beginning, because we knew that lithium nitrate has this healing, or I can call it also healing formation of the passive film, but it's very good, it forms very good passive film. And if there are some new passive film formation, there will be enough salt in the pores of the cellulose which can heal the further degradation of the metallic lithium. So after some optimization, we came with the optimal configuration. And you can see here a top-down view and then cross-section. Actually, we are now currently working with the coatings between 2 to 3 micrometer, which are pinhole free. And on the top of you can see only silica. And if we cycle this, in this case, is in ether-based electrolytes, and comparing this, so this first black curve is non-protected lithium, then red curve is lithium with the coating based on the lithium nitride seleniated cellulose coating, and the green one is only with lithium nitride inside this electrolyte. It's 0.2 molar concentration. So you can see at the beginning, of course, there is an advantage of having nitride directly in the electrolyte. But then after 200 hours, we already see the benefits, and actually the black, without coating, we see only problems with the cycling. The cell with the nitride went into the short circuit, while this one keeps working for several hundreds hours more. And to understand now this property, we actually employed impedance spectroscopy, and simply we assembled a symmetrical cell, lithium-lithium, both lithium unprotected, both then with cell gas separator and using lithium nitride inside the electrolyte, and actually with both lithium protected. What we can see that there is a huge evolution of the impedance within 24 hours, so that actually creates some actually problems with the passivation. So this tail actually is also growing. While here we see more or less in the first 10 minutes or maybe first hour, we see some shift, but then this shift is stabilized. And that actually creates that, suggests that there was a formation of stable passive film after assembly. And then also after cycling, this is even more pronounced. So this semicircle, first semicircle actually, which is corresponding to charge transfer, actually drops a lot because there is a nanostructuring of the lithium, but we have another contribution because of the lithium diffusion through high surface area lithium and so on. While here you can see that there is a pretty stable also during the cycling. There is a small decrease of this first semicircle, again because of higher surface area available, but this second semicircle, which actually means diffusion, remains almost more or less constant. And that gives us also a possibility, this more or less constant layer gave us a possibility to measure also conductivity of the layer, which is reported here. It's 2 orders of magnitude lower compared to the compared to the liquid electrolyte. And also transference is quite low, and that's now we have actually activities going into the all solid state batteries by using polymers, single ion conductive polymers inside, which can improve the conductivity, which can improve also this resistivity of the interlayer. And just to show you that this interlayer actually works, so on the top is lithium metal, which was cycled in nitride containing electrolyte without protection. We see this black surface. We see also protected edges, and we see intergrowth of metallic lithium into the separator. While in this case, we don't see any intergrowth of metallic lithium into the separator, we see some small damage, some small black spots. But when we look carefully with FIP measurements, actually we see that the silicium is still on the top, and this actually silicium comes from the seleniated cellulose. But also actually there was a small growth or intergrowth of lithium during the deposition and stripping which shows that actually the area was active, but the area didn't create any high surface area lithium on the top. So there was no connection, so there was no penetration through the layer towards to the cathode material. So, and we believe that this is possible because cellulose, at the beginning, it was designed to prevent any growth of dendrites because of this intertwined configuration of the cellulose fibers. And with that, actually, we created some kind of network which prevents dendrites. But then with the salt inside, we worked with many different configuration of electrolytes, and we tried to understand this, why this conduction is working. And I need to mention already here that we don't see any dissolution of the nitrite out. Of course, there should be some, but there is not in detectable manner. So we propose that this interlayer actually works like a solvent in salt system. So it conducts lithium. It requires a solvent which can solvatate nitrite. We can solvatate nitrite, but and then lithium is actually conducted through the nitrite elements. Sorry for this disruption. And actually, that's the system that we are using right now. This salt can be changed. The salt actually can be exchanged with the different salts, as I will show later. But first, I would like to share with you these results from the anode-free system. So we can cover copper foil, and when we can run, then we can strip and deposit between the lithium, and you can see we can run with really high efficiency this cell, and with no morphology after 100 cycles developed on the surface, while using unprotected or electrolyte containing nitrite. You see that there is this again formation of high surface area lithium metal creation. So recently we are studying this more deeply in different combination of electrolytes, and also, so I will show in different combination of salts. And we are using methodology of using 1 milliamp hour current during and 10 hours charge deposition, stripping and deposition. And then we deposit again or strip again, and then we do short cycles, and then we check how much of lithium remained here. Those are efficiencies. Of course, this is different procedure compared to the literature, but for us, this methodology was established, and we are actually comparing this efficiency. So this 98.42% means that also from starting point to here, actually, we recovered, we lost maybe 1.5% of lithium in the configuration of electrolytes. Here is FSC-DHC, here is LiFeFSCI for DME. And moving even to some other electrolytes and even some other mixture of salts, you can see using, like what I can say, going to PC, it decreases the efficiency. We can add this fluorinated LiBOP. We can add inside, so to increase also, the aim is actually to increase a little bit more conductivity through the layer, but this work is still ongoing, and I hope I will be able to report it in near future. Next, of course, once when you have such system, you put that system against different cathode materials, and we try to test it in different environments with ether-based electrolytes, with carbonate-based electrolytes. For ether-based electrolytes, we selected as a cathode lithium titanate oxide spinel structure. It's not real cathode, but Just we wanted to show that this can be cycled for a long time, and compare with unprotected lithium and also electrolyte that contains lithium nitride. So this worked very well in 2000 cycles, and you can see still there's almost no sign of any penetration of any dendrites into the separator. And that methodology also, that protection layer, works very well with LFP chemistry, 2-sim cycling. 1000 cycles was achieved, NMC without problem, but of course it depends also about the quality of NMC more than the quality of the coating. So it means that we can cycle, we never tried the high voltage lithium manganese nickel spinel, but we cycled this configuration of the elements of the cathodes. And with that, actually, I would like to conclude in my first part. I hope I showed you that this is reasonably simple methodology that we have developed, and using renewable and abundant natural polymer with some tricks how to actually stabilize everything. We have achieved already quite significant improvements, but of course some transport properties might still hinder the usage, although we have tested also these protective layers with current densities of like between 5 and 10 milliamp per square centimeter, and still some energy can be obtained in combination with NMC cathodes. And now I will move to the second part of my talk, and I hope I will convince you that also the work that we are doing here is simple. It especially when you think about how to move that from the developed methodology, from developed sensors into the manufacturing. As I said at the beginning, our main focus is on dissolution of manganese, mechanisms, why manganese is dissolved in the electrolyte are known from the literature, so it's not aimed to go very deeply and to discuss this. But it's more, we wanted to check what is the quantity of dissolved manganese, and actually how this dissolved manganese involves during the cycling. And you can see here that there is a linear actually decrease of the capacity by with the cycling when you are using lithium manganese spinel, while somehow manganese dissolution is really the highest at the beginning, but then somehow it's not completely stopped, but it's the solubility is decreasing, and I see this a little bit more like a logarithmic function. But anyway, the quantity of dissolved manganese that we detected here, and if we correlate the quantity of dissolved manganese and capacity fade, we can see that actually manganese dissolution corresponds only maybe to the small fraction of the capacity fade. But of course, we know that manganese dissolution creates a lot of problem on the anode, and with where actually manganese is reduced, and then the SCI becomes more electronically conductive, and it has to be repassivated and so on, and that creates actually the higher degree of capacity fading compared to what could be expected from the manganese dissolution. There were many different approaches proposed in the literature. Most of them, they are based on the cells that cannot be actually further developed into the practical commercial battery cells. And that's why we decided in collaboration with colleagues from University of Pardubice to use technology, printing technology, and to print sensor on the separator. So actually, what do we have? We have this actually integrated circuit. we checked or we tested different geometries, and at the end, actually, we found out that this geometry, which fits more or less to the circle of the electrode, provides the best and the most reliable and most repeatable results. We actually also checked that this has no influence on the battery performance. And so now we have these two electrodes, and then we have a connection to the electrodes and contacts. And then between those two electrodes, we can put a sensing layer. So now you can imagine this sensing layer can be whatever you want to detect. If you want to detect dissolved manganese, then you put something that will attract, that will capture, that will coordinate manganese, or maybe some other transition metal that can be dissolved. You can put also another layer which can actually detect formation of fluorine compounds, or even we are actually discussing how to find, what to use to maybe to find some formation of hydrogen or formation of some gases within the electrolyte. On this sensing layer is put then between the electrodes, and in our case today I will discuss this imprinted polymer which can actually coordinate manganese, and by leaching manganese out, we have a now tool that if some manganese is dissolved, actually it will be immediately coordinated by this polymer. It can be used also, we can imagine this polymer as a scavenger for manganese capturing, and that's also another possible use of this polymer. And if we put this polymer in between the two electrodes and we check if this polymer has some electrochemical activity in the voltage window where the battery operates, we see that there is this GC means glassy carbon, and and that means that glassy carbon is covered with this imprinting polymer. We don't see any redox activity. But then we move to the electrolyte, which contains manganese dissolved inside. And if we put that against glassy carbon, this is this dotted curve, orange dotted curve, we see this classical two redox peaks, which are coming from manganese 2, manganese 3 to 4, 4 to 3, and 3 to 2 plus reduction and then oxidation. And so basically we see that this compound is active inside, but once when we put in combination with polymer, we see that manganese 3 to 2 plus reduction is somehow hindered, and it occurs with some polarization. And that's actually show us that manganese 2 plus, which is inside, will actually it has some resistance to be reduced to 2 plus. And so that gives us a hint that we might maybe measure some properties of the polymer which can serve us as a sensing indicator for the battery. So next, what we did, we cycled the cell with the sensor, without the sensor, but of course, in this case, without sensing layer. So we don't see huge differences. I think differences are within the experimental error a student can make. And then we moved to again back to the electrolyte that contains dissolved manganese cations inside. In our case, this was we put 10 millimolar concentration of manganese acetoacetonide inside the electrolyte. And actually, what we can see, if we are using electrolyte without any additional manganese inside, we see in impedance spectra repeatable result for 2 weeks. But once when we put manganese into the electrolyte and we repeat the same experiment with the sensor that has the sensing layer inside, we see some deviation in this mid-frequency region. And that actually corresponds to some additional capacitance and resistance, which is parallel to the sensing layer and glass fiber substrate, and actually and it can be only due to the presence of manganese ions inside the electrolyte. So one might have question already, how about other ions? If this is property of acetoacetonite, or this is really property of the manganese? Here, actually, again, is without any additional salt inside the electrolyte. If we put lithium acetoacetonate, you see there is no difference. So impedance spectra are repeatable. If we put manganese, that's what I showed, and I don't have here results for the nickel, but also nickel is sensitive, but maybe less sensitive compared to the manganese with actually this imprinted polymer that I showed. Also, when you are cycling NMC electrode, we can see that there is some shift in this mid-frequency range of the impedance spectra. So I already mentioned that we cycled electrodes, and here I will actually show you the cycling of lithium metal, lithium manganese oxide spinel structure battery with the sensor inside. And so what we can see, we cycle those batteries with different C rates, and actually with the slower rates, we see faster response of the sensor. And actually, this can be understood in two different directions. One is cell is much longer in the high oxidation state, and that actually we know that dissolution of manganese occurs at this high oxidation states, and so it's correlated with the lifetime of the cell at this high oxidation C rates. Compare if we are cycling faster battery. And this brought me actually perfectly in 45 minutes to the end of my discussion. So here I will not go through all these conclusions that I prepared, but somehow the methodology of printing sensors is very simple. Those sensors can be printed roll-to-roll process. They can be printed even on the inner housing of the battery cell, and then connected through the cables, or maybe even wireless to the BMS. So that's actually simple and methodology that does not need also adoption of already existing manufacturing process. And it can be adapted to different compounds, or maybe even maybe in the future, I'm dreaming to show you even some kind of blend of experiments that we can detect several different properties in a reliable and detectable way. But of course, with this first part, we are now moving to the direction that we can not only qualitatively detect, but also quantitatively detect dissolved manganese in electrolyte. And yeah, of course, at the end, I would like to thank you for your attention, and also many group members that actually didn't contribute directly to this part, but they are contributing to the success of European science, NIC, and also actually overall battery science. Thank you.